In today's lecture, we're going to start Chapter 5, which is all about sensation and perception. And so it should come as no shock that we're going to start with some definitions. Sensation is going to be the stimulation of our sense organs. Our sensory receptors, when they're picking things up, when they are stimulated, that is creating sensation. Perception is going to be a little bit more filtered. Perception is going to be the selection, organization, and interpretation of that sensory input. So perception is what we make of the things that we are sensing. So sensation is the more basic version, and perception is what we do with that information once we get it. Now at the very beginning here, we're going to talk about psychophysics, which is the study of how physical stimuli are translated to psychological experiences. So this is what this chapter is all about, understanding how different physical stimuli, things like light and sound waves, are translated into something that we can experience, something that we can perceive. So how do we go from a stimulus in the world to something that we can sense and then perceive as we interpret those sensations? And one of our big names for this chapter is going to be Fechner, who was studying psychophysics back in the 1800s. Now, before we can get too in-depth about our different senses and the different systems of senses that we have, we're going to start talking about some of the rules and ideas that are going to carry across all types of senses. So we're going to start out by talking about what is a stimulus. And a stimulus is going to be any detectable input from the environment. We've used stimulus as sort of a catch-all term already in this course, and here we're just specifying that it has to be something that we're capable of detecting, something that we're perceiving, and it's any kind of input from our environment. So sound, light, things that are touching us, those are all stimuli. The singular is a stimulus, stimuli is the plural. And so if we're going to be talking about this detectableness of different stimuli, then we're going to be talking about our absolute threshold. And so for any specific type of sensory input, so we can talk about our vision, we can talk about our hearing, we can talk about our tactile senses. Those are all different types of sensory input. So for any specific type of sensory input, this is going to be the minimum amount of stimulation that an organism can detect. So our absolute threshold is the minimum amount of stimulation that we can detect. So if we're talking about the stimulus of light, this is going to be the absolute minimum amount of light that there needs to be before we can tell that there's light there. So if we're telling the difference between darkness and a source of light, how bright does that light have to be so that we can detect it? Now, because humans aren't very consistent, as we'll start finding when we talk about more of these different stimuli and how we perceive them, so we make up an arbitrary rule for our absolute threshold. And we can arbitrarily define it as the stimulus intensity where we can detect it 50% of the time. So when we can say that yes, there's a light, when there is a light, about half of the time, that's where we would call our absolute threshold. Now, the next slide actually shows us what our ability to detect a different stimulus is going to look like. And so this is kind of arbitrary again. So on this axis, we have probability of detection. So at the bottom, we are never going to notice the stimulus. And at the top, we will always notice the stimulus. And then in the middle here, we have our absolute threshold, which is we will notice the stimulus about 50% of the time. And then across this axis, we just have stimulus intensity. So this can be any stimulus. This could be light. So very low light is going to be very dim. And then up to sort of moderate levels of light is going to be brighter. It could be sound, where it's very quiet, up to louder. It can be smells, where there's no smell, up to it being very smelly. So this is going to apply to all of our different kinds of stimuli. And so here, we're going to have this sort of reddish line that runs through here. And this is showing basically what it looks like for most of our senses, where when there are very, very low levels, sometimes we're going to be able to detect them, but not always. And as they get more and more intense, our ability to detect them rises very quickly. And once we cross that 50% threshold, we've hit that absolute threshold, where we're calling that our minimum amount of intensity to be able to detect it. And then from there, it's going to get very, very good at detecting it once we've crossed that absolute threshold. So we get very good at seeing things or hearing things or feeling things once we've crossed that threshold. And then this blue line is showing kind of how it mathematically works when we talk about that threshold. So people think of it as before you cross the threshold, you have no detection, and then after the threshold, you will always see it. But in reality, we're just a little bit closer to this red line where we can sometimes figure it out when we're below the threshold, and we're going to miss it a little bit after the threshold sometimes, but for the most part, that threshold is our cutoff. And I include this chart from the textbook, not because it's useful, but because it seems like a ridiculous way of measuring some of these absolute thresholds. So if our sense is vision, the absolute threshold for something that we can see is a candle flame seen at 50 kilometers on a dark, clear night. I don't know who decided to measure that, but there is the absolute threshold for vision. Or for taste, you can taste 5 milliliters of sugar in 7.5 liters of water, in case you were curious. So these are interesting, but they just show you that each sense is going to have a different threshold. And even though we can talk about sort of an average threshold for human beings in general, each person is going to have different absolute thresholds, and our thresholds can change throughout life. So we'll start seeing a little bit of that, especially when we start talking about hearing, because our ability to hear changes dramatically as we get older. But that will come later in the chapter. So now, if we've talked about our absolute threshold, how much intensity we need to be able to tell the difference between something and nothing, the next term is kind of similar to that. And this is our just noticeable difference. Sometimes it'll be shortened to JND, or you'll sometimes see it called a difference threshold. And so instead of our absolute threshold of telling a stimulus from no stimulus, a difference threshold is the smallest difference in the amount of stimulation that a specific sense can detect. So, how much heavier does an object need to be for you to tell that it's actually heavier than the other object? So, if you hold out your hand and you have 2 weights placed in your hands, if one is just a little bit heavier than the other, can you tell the difference? And how big the difference in the 2 weights needs to be is our just noticeable difference for weights. And we could think of this as if you're looking at a screen and there are 2 squares on that screen of varying brightnesses. How different do they need to be before you can tell that they're different brightnesses? So that's our difference threshold, or our just noticeable difference. So how big a difference until we just notice that there's a difference. And all of these ideas are going to be interconnected with what's called Weber's law. Though Weber was German, so the pronunciation on that will differ, I'm just very poor at pronouncing German, so we'll call him Weber here. So the size of a just noticeable difference is a constant. So Weber's law is saying that there is a constant value that is proportional to the size of the initial stimulus. And so you could go in and calculate this Weber's fraction for each of our senses, but again, a little beyond the scope of our course here. What we're going to get out of this is the idea that if we hop back to our example here, so if you can tell the difference between 500 grams and 505 grams, if this initial weight was heavier, say this initial weight was 500 kilograms, you wouldn't notice a 5-gram difference, but maybe you would notice a 5-kilogram difference. So there's a scale where as the initial weight gets heavier, it needs to be a larger difference for you to notice that there's a difference. So as we scale up, that constant, that amount by which it needs to be larger, based on how large the initial stimulus is our Weber fraction. And of course, these constants are going to differ depending on the type of sensory input, kind of the same as everything we've talked about. So with sight, we're going to have one Weber fraction, and with hearing, we'll have a different one. But within a particular sense, it's going to be pretty consistent. Now, I'm aware that this is a little bit of an abstract concept, so I will highly recommend that you pause the video right now, and I have put this YouTube video up on our e-class, and this is one of the best videos I've found for illustrating this concept. It is just a guy sitting in his car using sound to illustrate an absolute threshold, the just noticeable difference or difference threshold. And he even explains our Weber's constants, or Weber's fractions, just to give us a more interactive explanation of the concept. So, highly recommend that video, and after you've watched it, you can come back, and we'll keep on. Now, we're used to measuring things using what are called absolute scales. So if we measure something like a distance, and we're measuring that in meters or centimeters or miles if we're going wild and crazy, those scales are going to be absolute. A meter is a meter no matter where it is. But as we've started seeing with this perception thing, it isn't always going to be equally applicable. So with perception, everything is relative. We can't rely on absolute scales. So we've kind of seen this already looking at our threshold, our absolute thresholds, and even our just noticeable differences. Things change depending on the intensity of the stimulus. And we have, of course, another law that tries to sum this up for us. So Fechner's law states that subjective sensation is proportional to the logarithm of the stimulus intensity. And that is an awful, awful definition. But what it means is that with constant increases in our stimulus intensity, smaller and smaller increases are perceived in the magnitude of that sensation. So even though we're having the stimulus intensity increase consistently, we have this absolute and consistent increase in brightness or loudness or smelliness. Our perception of that increase gets less and less over time. So we can actually draw this out here. So if we have a diagram kind of like this, and at the bottom is the actual intensity. So this is our absolute intensity. And then over here is our perceived intensity. So this is what we think it is that we're seeing. And this is sort of the waves of light that we're actually seeing. So as we have a consistent increase in actual intensity, our perceived intensity actually plateaus, kind of like this. So that gradual leveling off is very similar to what we saw when we looked at the graph back when we talked about our absolute threshold. So even as we get this consistent increase just like we saw in the video, a consistent increase in volume, even if you turn the volume up by 1 tick each time. So as you go from 4 to 5, 5 to 6, 6 to 7, as you get higher, that 1 unit increase doesn't sound like it's as big of a change. And eventually, it sounds like there's no change at all. So this is all described by Fechner's law, where we're seeing this gradual plateauing, or a logarithmic curve, in this difference between our perceived intensity and the actual intensity of a stimulus. So that's what the law, or that's what Fechner's law means here. Now, we can make some use of all of this weirdness between perceived and actual intensity, and perceived and actual differences, and even our absolute threshold. We can sum it all up in signal detection theory. And signal detection theory says that our detection of a stimulus is going to involve decision processes as well as sensory processes. So it's not just what we are taking in from our surroundings. It's just not the sensations. It's also our perception of those sensations. So there's some internal decision-making process that lets us decide if we have seen something or not, if we have heard a difference in volume or not. And both these sensory and perceptive processes are going to be influenced by lots of factors, and these factors are going to be things other than stimulus intensity. So stimulus intensity definitely plays a huge role, but there's more to it than just that. And so we can illustrate that over here with this diagram. So let's set the stage first. Imagine that we have an undergraduate research participant who's shown up to do their research participation, and they're sat in front of a computer monitor, and they're told that on the screen there's going to be a flash of light, and their job is to hit a button if they see a flash of light. If they don't see the light, they don't push the button. And that's our setup. So either there is light on the screen or there's not light on the screen, and they push a button to say when there's light on the screen, and they don't push the button when there's not light on the screen. Sounds pretty simple. So if we have this diagram here, we can look at our subject's response. Either they've pushed the button to say there's a light present, or they don't push the button and they're saying that the light is absent. And we can compare that to the actual stimulus. Is there actually a light on the screen? Do they say that, or is it actually present? Or is there no light on the screen? Is it actually absent? And so we have a couple of kind of mundane situations. If there is a light on the screen and the participant says there's a light on the screen, you have a hit. They saw the thing that was there. Not very exciting. And similarly, you can have a correct rejection if there isn't a light on the screen and they say there isn't a light on the screen. Cool. But now it gets interesting because we have two ways that we can be wrong. The first is that when there is a light on the screen, but we miss it, we say that it's absent, we don't push the button, even though there was a stimulus on the screen. So this is called a miss because there was a stimulus, we just didn't notice it. So in this case, this could be maybe the stimulus hadn't quite crossed our absolute threshold. Or maybe there's something perceptive going on where we're not aware of something. But either way, we didn't notice that it was there. The other cool way we can be wrong is if we say that there was a stimulus, we push the button, but there wasn't anything on the screen. So this is a false alarm, where you didn't actually see something, but your brain has convinced you that you did. And this one is really cool for psychologists because you conjured this stimulus or the idea of a stimulus out of nothing. So we care most about either these false alarms or these misses because they're giving us information where the actual situation doesn't match our perception of the situation, which is pretty cool. And then this leads us over to another category, and this is the idea of subliminal perception. And subliminal perception is the registration of sensory input without conscious awareness. So this is basically a miss situation. So there is actual stimulus present. There is something there that we could see or hear, but we're not aware that it's there. So we would say that it's absent. And so what's cool here is that with subliminal perception, we're registering that sensory input. We are having it enter our brains because our sensory registers are aware, or they're noticing the thing. So our eyes are seeing the light, or our ears are hearing the sound, but we don't have conscious awareness. So our brain hasn't made the connection that we have seen or heard something. So for an example of a subliminal message, maybe someone's going to flash an image up on the screen very quickly, faster than you could be aware of a change happening, but the information that was flashed to you has now entered your registers. It has entered your not quite consciousness, but it's still in your brain somewhere. And this all started back in the 1950s with a man named James Vickery. And he had this idea that he'd go to a movie theater and he would flash on the screen before the movie just a frame or two of the phrase, "Eat more popcorn." He also had another theater that had the phrase, drink more Coca-Cola. And he would then record the sales in that theater of popcorn and Coca-Cola. And when he published his work, he reported this massive increase in both popcorn and pop sales. And as you can imagine, his findings took the world by storm. People were terrified. The idea that a simple image flashed on the screen that you weren't even aware of seeing could so strongly influence your behavior scared people. And of course, people who were involved in marketing, people at big corporations, they were thrilled at this new idea of ways that they could sell their products. And so around the world, many countries started releasing these bans, these laws against using subliminal messaging. And to this day, it's still illegal to use subliminal marketing over in Europe. Now, this is where we take a step back, and I tell you that this wasn't actually something that was observed. So James Vickery did the experiment, and he published that paper, but he fabricated his data. So his massive difference in sales was all a lie. And so he created this marketing, this idea of something that was having this huge influence on our lives, and it was all false. So since then, laws have been relaxed here in North America, so it's no longer illegal to use subliminal messaging. However, our current evidence kind of says that there's no reason to use subliminal messaging. It says that there are some forms of subliminal perception that can subtly influence our behavior in very particular situations, but in most cases, instead of using subliminal messaging, an advertising company would be much better off using a giant poster stationed outside of your house. They're much more likely to convince you to buy a product if you can actually see and evaluate their advertisements. So subliminal messaging isn't all that helpful. So some of the more recent studies looking at subliminal messaging where they've managed to find an effect are a little bit less exciting, I would say. So this one here was looking at trying to get people to drink Lipton iced tea. And it's an interesting paper to read, but their take-home message was if they had participants who were very, very thirsty, and they were restricted between picking iced tea or water, they could get some of them to pick iced tea sometimes. So it was a very small effect, and it only worked in these very restrictive circumstances. People have had a little bit more luck with subliminal messaging influencing us when we start looking at things like mood. So for this study here, they were looking at the idea of flashing attractive faces subliminally on a screen to make people adopt more of a jealous or protective behavior. And they were a little bit more successful at that. And so again, they can't make you go from perfectly content to insanely jealous, but they can make you just a little bit more defensive in your motivations. So again, our take home here is that subliminal messaging can have an effect. It's just not a very large effect. So for marketing purposes, you're much better off to go non-subliminally. Now, our last general concept to touch on before we get into our specific senses, our specific breakdowns of the different senses that we have, is going to be to talk about sensory adaptation. And sensory adaptation is a gradual decline in sensitivity due to prolonged stimulation. So, over time, as you are exposed to the same stimulus, you are no longer as sensitive to it. So it's say you're spraying cologne in the morning or perfume. So you put on a spray and it smells really strong for a little bit, but by the time you're ready to leave the house, you don't notice the smell at all. The smell hasn't actually gone away, you've just adapted to the smell. So you have become sensorily adapted to that situation. Febreze does a number of really great commercials where they call this that you've gone nose blind, where you can't smell a smell because you've been exposed to it for so long. And those are a fantastic and entertaining way to illustrate sensory adaptation. So if you're on YouTube anyways, looking at some of the videos for this chapter, I'd highly recommend going down that YouTube hole for a little while. Now, sensory adaptation is itself an adaptive process, so it's something that's beneficial to us. So this makes us aware of changes in our environment rather than things that are constant. So if we think of humans out in the wild trying to make a living as hunters and gatherers, you don't necessarily care that there are lots of birds chirping because they're constantly chirping, but maybe you would want your attention drawn to when they stop chirping. When they go quiet, that's telling you more than when they chirp for the whole day. So we are benefited by noticing these things that change in the environment, but it makes less sense to be constantly aware of things that are constant. And our sensory adaptation can happen for all of our senses. So we are much more attuned to noticing differences and changes than we are to notice things that are going to be the same.